in theoretical physics and mathematics. Generally speaking, almost always, theoretical physicists never prove anything. What they do is calculate things. And of course, you try to generalize from calculations in specific situations. And to a certain extent, this is what this talk will be about. And of course, being a theoretical physicist, you do things which any self-respecting mathematician would throw up their arms in horror about, and I apologize for that in advance. But what I want to talk about is that there is a sort of wide range of phenomena which can appear in scalar field theories, which I think are interesting from a theoretical physics point of view, and possibly in the future might even be interesting from a proper mathematical point of view. And the work I'm describing here was done with Andy Sturgio, collaborator of mine, but it's also related to some recent work by Slava Richkov and Andy themselves. Anyway, the motivation for this kind of subject, which goes back a long way, I mean, I should emphasize here, by the way, that quantum field theory in about 8 years' time will celebrate its centenary, and a lot has changed in quantum field theory over the years, but the major change happened in the early 1970s in relation to the work by Ken Wilson primarily. And Ken Wilson effectively did two things. One was to talk about the role of scales in quantum field theories and how one needs to understand what happens to quantum field theories as you change the scale at which you look at the theory and so on. And that's a primary subject of interest perhaps to the whole meeting here. But he also did something else in Michael Fisher, was to introduce something called the epsilon expansion, which is a very theoretical physics type thing, which I'll talk about in a short while. And this is something which has had a huge resurgence of interest. I looked up all the citations of the paper by Wilson and Fisher, and roughly speaking, it was 10 or 20 a year from about 1971 onwards, which is an impressive for a continuous thing, but in the past 4 or 5 years it's gone up to about 50 a year. Anyway, the motivation here is related to something called the bootstrap, which has been around in its modern form for about 10 years, and this is a way of looking at theories which have conformal symmetry. And with conformal symmetry you have a lot more constraints on the theory, and in 2 dimensions the constraints are extremely strong, which more or less allow you to solve the theories in least in specific cases. That's no longer true in higher dimensions such as 3 or 4, but nevertheless you can actually do a lot of work and find very good results in, for instance, the Ising model in 3 dimensions. And when you apply the bootstrap, what you do is that you say that there are certain operators in the theory which have low dimension. You impose a certain symmetry. In the case of the Ising model, it's just a Z2 symmetry, but there are more complicated symmetries that you can impose. There is a theory which has involved n component fields and which has an orthogonal symmetry. And once you impose certain restrictions on the operators, you can find very strong constraints on what are called the scaling dimensions of the operators, which effectively determines how the 2-point correlation functions of the relevant operators behave. Now, if you have any given conformal field theory, one of the things you can do is to look for operators which are relevant. Relevant means that the operators in the theory have dimensions less than d, which is the space-time or the spatial dimension that you're interested in. And if you add such an operator, assuming it's a scalar, to your original action, then the theory will evolve under changings of scale to another theory. I mean, if they're irrelevant, as you change the scale and try and go towards large distances, they will come back to the original theory, but if they're relevant, they will go to some other theory. And they may or may not lead, under renormalization group throw, to new fixed points. And what I'm going to talk about here is what are the possibilities that at least we know about in theoretical physics as to what potential fixed points may arise. Now, Of course, in 2 dimensions, one of the things which, again, if you're dealing with theories with Virasoro central charge c less than 1, and also they're unitary, these theories are essentially fully classified. I mean, one of the goals one would like to have in the context of a sort of theoretical physics, and actually this would be relevant to the real world, is what fixed points are there, for instance, in theories in 3 dimensions, and we're some way off coming anywhere near answering that question. So one of the things that you would have to be able to do that is to say, if you have any given theory at a fixed point and you perturb it by a relevant operator, what other theories can you reach by renormalization group flow? Now, what tools do we have to try and address such a question? And we're somewhat limited. The bootstrap is very good if you know something to start with in determining, actual values of scaling dimensions of operators and other properties of the theory. It's not so good as a sort of search device, because whilst there have been some hints of conformal field theories, it really only finds theories which in some sense you already know are there. And what I'm going to describe here is what can you do with what's called the epsilon expansion. Now, the epsilon expansion is something which you can apply to theories in continuous, it doesn't work on a lattice or anything like that, but you can at least formally apply it in the context of perturbation theory. And generally speaking, in theoretical physics, almost everything we know about quantum field theories is obtained by understanding the perturbation expansion and trying to show that something is valid to arbitrary orders in the perturbation expansion. And then you tend to say that this will be true for the full theory as a whole. So the point is that you change the space-time dimension to some value which is non-integer. Now, of course, this is something which is at least somewhat, that's very annoying, but see whether we can get rid of that. Sorry? That's the wrong one. Okay, there we are. Anyway, so the point is that Wilson was the first, Wilson and Fisher were the first people to propose this idea, and the point about this is that within the epsilon expansion you can actually find fixed points in many situations relatively easy, because you have an expansion parameter, and the expansion parameter is itself epsilon. Now, of course, such an expansion is something which, if you're a physicist, you just go ahead and calculate, but, does it have any sense? Now, of course, in any quantum field theory situation, any expansion is an asymptotic series at best, and therefore, one has to worry whether this makes any kind of sense, but I shall try and say a bit more about it in due course. But the point is that after Wilson and Fisher in the early 1970s, 1971 I think, put forward this, there was a huge explosion of people working out this in a wide range of different symmetries, and this was in principle applicable to a wide range of physical systems which are at close to their fixed points. Now, the things that you can measure in physical systems, they are very hard to measure, but in principle you can measure things called critical exponents, which are in a certain sense universal. They don't depend upon the microscopic details of the theory, and these are the things which in principle you can calculate using what's called the epsilon expansion. And then over the course of time people were able to work to higher and higher orders in epsilon in a sort of brute force fashion, not in any sort of deep understanding of what's going on, and they sometimes got results which were pretty good. Now, the point is, I'm saying a bit here about what the epsilon expansion is, and let's take as the canonical example a 5 to the 4th theory, and we imagine that it's in 4 minus epsilon dimensions. See if I can get rid of this stuff at the top.
Maybe if you just move the cursor down.
Yeah. There we are. Okay, so the point is that, we have to go back now. So the epsilon expansion was invented by them, and the point is that in phi to the fourth field theory, if the phi to the fourth operator itself has scale dimension delta, delta is the universal symbol used for the scale dimension these days, then this is if you're below 4 dimensions, this operator is relevant. And one way of showing this is in terms of what the beta function of the theory is. It starts off, beta function is basically a vector field on the space of couplings, and it defines the flow of the theory under renormalization group transformations. Now in this particular example, there's just one coupling, and so it's rather trivial, but nevertheless in a more multidimensional sense, which we'll discuss later on. Now the standard prescription here is that we choose the beta function to have this particular form, and there's a degree of arbitrariness in this because the theory should be invariant under arbitrary redefinitions of the couplings, because we're dealing with a sort of manifold of which the couplings themselves are just certain coordinates on the manifold. And we can make a choice that the beta function has this form where the dimensions only appear in the first term. Now the point about this, that you can calculate everything perturbatively, and at least in some theories, and for instance in the phi to the fourth theory, you have arguments which tell you what the asymptotic form of this function is for arbitrarily high powers of the coupling. So we have a theory which, in this particular example, we have some kind of factorial growth. Everything grows factorially, if not faster, with higher orders, and of course the beta function here, the coefficients grow like some factorial, and there's a known coefficient, Cn. So the point is that this knowledge of the high order asymptotic behavior means that you can kind of build this in to some kind of asymptotic resummation of the whole expansion if you know the first few terms. However, one thing which only became apparent in more recent years, that such a theory, if you move away from integer dimensions, has operators in it which have negative norms. So it's not a unitary theory, and as an example of that, you can consider a theory, for instance, which involves products of 5 of the scalar fields phi with bunches of derivatives, and you anti-symmetrize over 5 of them. Now if you anti-symmetrize over 5 indices in 4 dimensions, then this thing must be identically 0. But within the framework of analytically continue in the dimension, this is not got to have 0 norm in higher dimensions. It's a perfectly bona fide operator in 5 dimensions. It will vanish in 4 dimensions, and if you compute its norm, you will find that it has a negative norm, for instance in dimensions between 3 and 4. And of course you can construct arbitrarily many such operators. They have rather large scale dimension because they have quite a large number of derivatives, but nevertheless they clearly show that the theory is not going to be unitary once you try to move away from 4 dimensions, for instance. How this relates to reflection positivity, I'm unclear. Maybe it's a trivial statement that reflection positivity will break down, but I'm not clear immediately of any direct connection with that. However, but the point here is that what I want to try and discuss is whether or not we can draw any kind of general conclusions about the behavior of the theory, of these kind of theories in general. Using things like the epsilon expansion. The epsilon expansion from a theoretical physics point of view is well defined, and it's, if you like, a way in which we can search for potential fixed points. And the idea would be that you start with a certain number of fields, n of them, and look at quartic potentials and assume that there's some kind of symmetry of the theory, and then the idea is that you have to write down the most general quartic potential, which is possible subject to that symmetry. That symmetry has to be some kind of subgroup of ON, because that's the maximal symmetry that you can have for n scalar fields. You calculate the beta functions and various other properties, and you may have many couplings, and the question then is, what are the beta functions? You'll have an n-dimensional space. Well, I mean, there will be, depending on how many quartic invariants are, then there will be that many couplings in the theory, and you have a multi-dimensional space, and you look for the renormalization group flow within that space. Now, what I've done at the bottom is what happens when you have the maximal symmetry, and here I've written down the beta function to lowest order, and so you can solve in principle for the coupling at the fixed point, and it's an expansion in powers of epsilon, and I've given the first term, which is rather trivial, and there's the next term, and in fact people now have calculated this up to sixth order. So anyway, what I've described here is what you can get for the case of different theories with different ends, just as an example of how the epsilon expansion works and how the epsilon expansion works. And so the things you're trying to calculate, at least at the first go round in this, are what the various critical exponents are. And in simple models there are the so I don't know whether I can get rid of this thing at the bottom, but still, well, anyway, so the point is, so eta, nu and omega are things which are in principle measurable, and they're related to the scaling dimensions of the various operators which appear at the fixed point, and also to the spatial dimension. And I've listed some of them below, and the bootstrap, which involves pretty high performance computers, comes up with various numerical values, and then in the last couple of years people finally got the perturbation theory to work to 6 loops with something like 10,000 diagrams, and again that involves a large amount of computing power. And also you're using knowledge of the asymptotic form of the expansion of the beta function and other properties to be able to sign. So this is not a naive epsilon expansion, you're using information about the high order behavior, and you can see that it's pretty good. The bootstrap, at least in many cases, is very better than the epsilon expansion. I list 2 cases, n equals 1 and n equals 4. For the bootstrap, each value of n you have to treat rather differently. For the epsilon expansion, it's just a matter of shoving in the relevant values of the parameters. And of course there are lots of other things you can calculate, but these are the illustrative things. Of course the actual numerical accuracy goes down when you go to higher values of n, and also to operators which have a higher dimension. So the operator here, which is the highest dimension, is the 5 to the 4th operator. Anyway, the numbers are not so important. They're interest to people doing physics, but nevertheless they just illustrate of how different methods can come up with results which are in pretty good agreement. Anyway, the critical thing is that if you consider the theory under perturbation, now once you have a given theory, finding out what the spectrum of operators are is in principle a linear problem within that theory. And then you want to address the question of whether or not there are relevant operators through which you can perturb the theory and then maybe get to another fixed point. So in the case of the ON theory, which is the maximal symmetry you can have if you have n fields, if you take any perturbation, so we're interested in perturbations which are quartic polynomials in the basic fields, and of course you can classify them according to the representations of the ON group. In fact, there's only about 3 possibilities, but if you take a perturbation which involves a symmetric traceless tensor, this becomes relevant when the value of n is bigger than about 4. I mean, the precise value is depends on the dimension you're in, but roughly speaking it's 4. And then if you perturb by such an operator, you're going to flow under renormalization group transformations away from the original fixed point, and the symmetry will be broken instead of having an ON symmetry, you'll have a subgroup H for which Dijkl is some kind of invariant tensor. And then the interesting question from a physics point of view is, where do these perturbations flow to? Do they flow to new fixed points, which the couplings remain small, or you can imagine a scenario in which the couplings become larger and larger and the whole approximation breaks down. So a fixed point is only meaningful in this context if the couplings remain small and of order epsilon in this kind of framework. Now, of course, if you take a perfectly arbitrary set of couplings here, there are a very large number of potential fixed points, and the ON symmetry may be completely broken. The minimal symmetry that you can have is Z2, because the theory is always going to be invariant under reflections of the fields phi goes to minus phi. And so, but there are a lot of subgroups between ON and Z2, right? And so, therefore, you know, having some higher degree of symmetry will allow you to have other potentially interesting fixed points. Now, one of the things which has become more apparent, though again people knew about this a long time ago as well, is that there is a certain quantity which you can define on the space of couplings, which nowadays is called an A function, and which I've written here, well, its simplest form. So of course all these things go on to arbitrary orders, but here I've written it down to lowest order in the couplings, where we have a term which is quadratic and a cubic term. And the point about this is that the actual the beta functions of this theory are now essentially tensors, beta ijkl. They're given by the gradient of this quantity with respect to the derivatives with respect to the couplings. And the point is that this function decreases as they are. So T is renormalization group time. As T increases, you're flowing towards large distances or the infrared limit, and so it decreases, and furthermore, at any fixed point of the theory, the beta functions vanish. And so that at a fixed point, there is a sort of balance between the two terms here, and this is what the value of the quantity A would be at the fixed point, which is given by where these beta functions will vanish. Now, of course, this is all done to lowest order, but nevertheless, it can be extended to arbitrary orders. Now, one thing to note here is that this quantity A is clearly not bounded below because you have a cubic term in it, but nevertheless, in general, you want all these couplings lambda to be essentially positive because you want the potential V itself to be bounded below. The theory makes no sense if the potential V is unbounded below, and therefore this quantity A should be effectively bounded below, and of course at higher orders there will be higher order terms which will potentially make this more evident. Now, the point is that what you can show just by using the equations which I've written here, just the fact that this lambda is cubic and you solving the fixed point, that there is a lower bound on this which is just determined by the number of fields which are present. I mean, this was shown in this recent paper by Slava Richkov and Andy Sturgio, though it was known to be true in some particular cases previously. Now, the point is that if the bound is saturated, then there is an exactly marginal operator in the theory. A marginal operator is one which is got a scale dimension equal to the dimension of the theory which you're in. And this is the scenario which happens where we have fixed points which annihilate each other. Generally speaking, one of the things, of course, which this existence of this quantity A demonstrates is that if this quantity decreases monotonically, it avoids chaotic behavior, because once you're in a theory with multiple couplings involving certain first-order differential equations, as one knows, that it's not necessarily the case that one ends up at a fixed point. The thing may become just chaotic, or it may just go on to limit cycles and so on. But nevertheless, the existence of this function A shows that the theory must essentially go to a fixed point, or it can go to a situation where the couplings just become larger and larger. But when the bound is saturated, you're at a bifurcation point of two fixed points, and of course, as parameters change, so typically speaking, let's suppose there's some parameter x in the theory. It may be quantity such as n itself, or maybe some other parameter in the theory. Then typically speaking, you would have a square root branch point is this parameter, and so that the couplings here would only be present when x was larger than x0, and as x goes to x0, the two fixed points will annihilate. There are some situations, for instance, when at one of these fixed points you may get decoupled theories and so on, but once x is less than x0, the fixed points move into the complex plane. They still affect the renormalization group flow of the theory, but the theory can't end on such fixed points, assuming the couplings all stay real. Now, the space of all couplings is not a straightforward one to analyze. The number of possible couplings grows with n, roughly speaking like n to the fourth, and so in order to make such problems tractable, one needs to try and restrict to some submanifold in which you impose some subgroup of symmetries of H, and so that restricts it to a more constrained problem. Now, in order for this to remain sort of, if you start with a finitely many couplings, then the renormalization group flow can generate new operators, in which case you have then to put new couplings into the theory to begin with. But let's consider the simplest case, whereby instead of, you introduce two couplings in the theory to begin with, say lambda and g, where this dijkl term is the thing which will perturb the theory to go to a new fixed point. And now, in order for such a theory to remain stable under a renormalization group flow, you have to impose constraints on these tensors D, and here I've written the simplest constraint. I mean, effectively what you're saying is that you have a symmetry H in which there is only one additional invariant quartic polynomial besides the ON symmetric one. The first term, the phi squared or squared, is symmetric under ON. The second one breaks the symmetry to some subgroup H, and so in order for, and if we assume that's a unique object, which is a rank 4 tensor, invariant under group H, it follows that if you contract two of these D tensors, well, you may get some bunch of Kronecker deltas. I apologize, by the way, for having indices everywhere. It's what physicists do, but nevertheless. Anyway, but you can then get this tensor must close on itself. Now, the scale of these things is kind of arbitrary, but the physics depends on the parameter b squared over a, because that's where the scale dependence that drops out of the arbitrary normalization of d will drop out. You can set a equal to 1 if you want. Now, in general, there may be several such quartic polynomials invariant under H. If there are several, then you have to make these into kind of matrices and so on. But now, of course, these quantities here, there are constraints which you can, just by computing norms and things like this, you can show that for any such tensors there is a bound between a and b, at least if n is bigger than 2. And so for any n, there's also any finitely discrete number of possibilities for this quantity here.
Can you back up? I didn't see what a was.
Well, a is just the normalization of d, effectively. You can set a equal to 1 if you want to. But yeah, sure.
Okay, in this case, the group, what is the group H in this case? Is it ON minus 1 or something?
No. Well, I'll give examples in a while, what the theories are. I mean, that might be one possibility to choose, but I'll describe some particular examples in due course. Okay. Anyway, so the point is, But one thing is, for any given n, there's only a discrete number of possibilities. In fact, I mean, a slightly non-trivial problem would be to find all possible solutions of this equation, or invariant tensors under On. I mean, I know some specific solutions, but a general solution, you know, is not, it may be obvious to somebody who knows more of the background here, but nevertheless, it may be that there's only two solutions for the specific thing. I mean, I know two solutions which exist, but nevertheless, whether there are any other possibilities, I don't know at present.
So,
Yeah?
so you've got 4 parameters to choose, lambda, G, A, and B, and the subgroup H.
Well, you've got the subgroup H to choose, but the fact is that the example I've shown here is one in which H is such that there is a single quartic polynomial. Okay, I mean, you can generalize, I mean, if there are several polynomials here, then of course this G will have to have an index associated with it, running over the number of different possibilities there are. So, I mean, this is kind of reminiscent of what you do when you classify Lie algebras, but it's slightly different from that. Anyway, so, but there's also constraints on B and A. Not all possibilities for B and A will lead to new fixed points. You have to impose the condition that n is bigger than 4 plus 9b squared over 4a. Now, of course, that clearly shows that n must be bigger than 4 in this case. But if b squared, I mean, b and a will themselves depend on n, and so this inequality might not be realized, and there are situations when it isn't realized. Well, anyway, let me give you some particular examples of solutions of this. So one example would be to take n-dimensional regular polytopes, which are generalizations of Platonic solids, and let's suppose that you say the vertices of these Platonic solids are given by vectors. I here is an index which runs from 1 to n, and alpha tells you where the vertices are. And then you can define a particular invariant polynomial by this particular equation which I've written there. Now, and the second term is just determined by the requirement that we assume the whole thing is traceless on any pair of indices. Now, for n bigger than 4, there are some only restricted number of Platonic solids. There's the hypercube, an obvious generalization of the cube, 2 to the n vertices, the hypertetrahedron, n plus 1 vertices, and the hyperoctahedron, which is 2n vertices. But 2 of these are dual to each other, and they give identical quartic polynomials. And so the symmetry group in the 2 cases, for the hypercube it's the Sn, the permutation or the symmetry group, semi-direct product with n copies of Z2, and in the case of hypertetrahedron it's the group which permutes the vertices of the hypertetrahedron. And so you can work out for these cases what are the potential values of B and A, and the hypercube itself saturates the bound which I've just described. Now let's consider the hypercube case, and let's suppose that we're dealing with theories in, roughly speaking, dimensions less than 4. Now, in this situation, the renormalization, there are 2 couplings in the theory which here are given by U and V, and there is a big difference between where in the theory where you have n less than 4 and n bigger than 4. So the different symmetries, so the Ising theory is where you have a decoupled set of scalar theories, and so you have a single fixed point which corresponds to the Ising model. The Heisenberg fixed point is the ON theory, or in this case, well, if n is 3, it would be the O3 theory. And the cubic fixed point is the one where the things get mixed up together in some fashion, and those arrows indicate where the RG flows to as you flow towards large distances in the theory. And so for n less than 4, approximately at least, you flow to the Heisenberg fixed point, which is the theory with maximal symmetry. But if n is bigger than 4, you flow to the cubic fixed point, where the symmetry is broken from ON down to this discrete theory, which corresponds to so there's a discrete symmetry which is left in that situation. And then the cubic fixed point, well again you can try it becomes stable when n is bigger than some critical value, and here I've given an expansion where you could carry this through to higher orders. For d equal to 3, roughly speaking n is equal to 3. We don't know the precise value of the critical value here, whether or not 3 is the stable critical fixed point, is the cubic point, or it's the O3 point. But anyway, this is a bifurcation point, and when we're at the critical point we have this sort of two fixed points merging with each other. So for instance, as you go from the critical value, the cubic point and the Heisenberg point will come together, because as you can see between these two pictures, the cubic point has moved from below the x-axis to above the x-axis, and so at some point the two will collide at a point, and so that's when the new symmetry emerges. Now, as n becomes larger, the cubic fixed point is no longer going to be the stable fixed point of the theory. As I said, once you're at a bifurcation point, the value of a takes its minimal value, so you can't go any lower there, but as you move away from the bifurcation point, there's some space to perturb the theory to get to a lower value. And for instance, when n is bigger than roughly 5, the tetrahedral perturbation becomes relevant. Now, other cases can be obtained. I mean, I talked about regular polytopes, but in fact, if you have solids which are not so much completely regular like Platonic solids, but just vertex transitive, which means that all the vertices of the polytope can be obtained from each other. They're all equivalent by the relevant symmetry group. Now, for each subgroup, there may be a fixed point which has some non-zero value of g, but the most stable fixed point in any situation will always be the one where take the minimum value of the theory. So, so for instance, if we take the theory which I've described, which has two couplings, and it wants to flow to the hypercubic fixed point when n is a bit larger than 4, but for larger n, this fixed point becomes unstable. By unstable, I mean that there are relevant operators which allow you to flow to other fixed points in the theory. Now, what I've described is one framework. You can slightly generalize this, whereby, for instance, you can add an extra tensor which involves some kind of additional symmetry, mixed symmetry. So that doesn't relevant to as far as quartic polynomials are concerned, because it will vanish if you contract W with all the scalar fields in the theory. But this still gives a two-coupling RG flow, but you can allow for symmetry breaking to continuous subgroups of ON, such as, for instance, if we take it can flow to some product of orthogonal groups divided by some Z2 symmetry or some permutation of these theories. The fixed point structure is similar, but clearly there are more possibilities. And again, as I said already, they may have bifurcation points whereby the thing becomes as stable as it can possibly be. I should add that all these operators, all these theories that we're discussing, will have polynomials which are quadratic, and you have to tune all those to 0, just like you tune the mass parameter in ordinary phi to the 4th theory to be 0 in order to get to a critical point. But not all values of m and n will give rise to critical fixed points. Now, this is an example of the ones which have been explored in the literature at various points over time. So the point is, here we have theories where we look for a certain number of quartic invariants, a certain number of quadratic invariants. The quadratic invariants always have to be essentially tuned to 0 in order to get to the critical point. And for instance, in most of these examples, there's just one quadratic invariant, which is phi squared itself. And then, of course, on the left are the theories which have different kinds of symmetries, or at least the names of them. So the symmetry group is listed down below there. So this is not a completely exhaustive set of possible theories because it's a rather complicated problem. Maybe this is a problem which has been solved in the mathematical literature, namely what are all possible quartic polynomials invariant under subgroups of ON, and how many such quartic polynomials are there. This is a set of examples in some cases, but nevertheless a general solution of this problem, at least in a form which I would understand, I don't know.
If you had a 5 form and a cubic term both, can you always get rid of the cubic term? Or
no, the cubic term can also be, well, some of these theories, I mean, the symmetries are such to preclude you can always remove the cubic term by fiat by imposing a Z2 symmetry. In some cases, if you break the Z2 symmetry, you can allow the cubic term, and for instance, the tetrahedral term has a cubic term which will be invariant under Sn plus 1 without the Z2. So all these invariance groups contains a Z2 in it, corresponding to reflection symmetry. In general, in condensed matter literature, generally speaking, having a cubic term is such that you don't have second order phase transitions, you have first order phase transitions. But this is perhaps more of a mathematical exercise. However, anyway, so the existence of cubic terms is not relevant from a standard perturbation theory because they don't feed back onto the quartic terms. Okay. In a more complete framework they might do so, but in the sort of naive epsilon expansion they're not relevant. Anyway, so this is one example. So all these things exist more or less for arbitrary values of n, but there are specific groups that you can get for particular values of n. I should say that every one of these particular examples have been explored at some significant length in various condensed matter papers, and they're all, at least in principle, relevant to real physical systems. Yeah.
Sorry, the equation you wrote earlier on the D, the quadratic equation on D, where does it come from?
Well, well, for instance, let's take this equation at the top here. Well, the assumption is that let's assume that there is a unique symmetric traceless tensor which is invariant under the relevant group. Now, if you contract two of the indices there, you form another symmetric. Well, you can form a symmetric tensor up to thisWijkl thing, right? So if you symmetrize over all the indices Ijkl, then the W term will drop out. And if there is just one such tensor, that's the only thing it can be, right? If there are several such tensors, it can be some linear combination of them. So W here fixes up the fact that W will disappear if you symmetrize over the indices I, J, K, and L.
Because I was confused. Do you first pick the group and then look for a tensor, or because you could also define H as the invariance group?
Well, you can do either, really. It doesn't really matter. I mean, in some cases, yeah. I mean, from the point of view of applying it to real physical systems, you assume that there's some kind of crystal which has some symmetry group, right? And then you look for invariant polynomials which are invariant under that symmetry. That's the traditional route in the condensed matter literature. Okay. I mean, of course, the crystal has got a very complicated structure and doesn't have full rotational invariance or anything like that. But in the continuum limit, where you're close to a fixed point, and the microscopic details are not supposed to matter, it's only the overall symmetries which are relevant of the theory. Okay. So, but anyway, it may or may not be an interesting classification problem. It's equivalent, more or less, to finding all possible subgroups of ON and so on. Anyway, so this is a set of examples which have been discussed with certain names associated with them. Now, the point is, so the risk of repeating myself, I'm just saying that the aim here is to find from a purely sort of general point of view, is find all possible subgroups H of ON, and then find all possible quartic polynomials which are invariant under this. Of course, different groups H may have the same set of quartic polynomials. A full analysis has been more or less done for n equals 4 or 6. There are lots of different possibilities, but a possible general classification at present is not clear, at least as far as I know. Not all possibilities, even when you've got them, can lead to fixed points in the epsilon expansion, because it depends on the parameters, for instance, in the simplest model B and A. You can invent theories. For instance, if you take a theory which involves symmetric traceless rank 2 tensor fields, you can write down a quartic invariant polynomial in this case, but such a theory does not have fixed points because the parameters don't lead to the sort of possibility of having that. But in general, when you have a theory with many couplings, there can only be one stable fixed point. All the other ones will have relevant perturbations. And I should also say that in general that there are no dead-end theories. A dead-end theory would, if you like, will be a theory which you cannot possibly perturb to flow to a different fixed point. That there are no relevant perturbations in it. All these theories potentially have relevant perturbations, at least as you change the parameters, and therefore you can flow to other fixed points. Well, come to the end. The point is, from a purely theoretical physics point of view, you can extend this to other theories in, for instance, 6 dimensions, or in a moment in 3 dimensions. In 6 minus epsilon dimensions, basically, if you're dealing with normalizable theories, you have to deal with cubic polynomials. So these things are not very interesting in some respects because they are clearly unbounded below, but nevertheless you can discuss them perturbatively, and you can, for instance, discuss a theory which has such a theory never has ON symmetry because there are no cubic polynomials which are invariant under ON, but you can consider theories which are invariant under ON minus 1, and then you can perturb them. In this case, there are fixed points when n is very large, roughly speaking 1,000, but these are unstable. Okay, but you can then consider various breakings, and basically the ON group breaks to some product of orthogonal groups. And there is a corresponding A function which decreases under RG flow, but there's no positivity, so the couplings become arbitrarily negative. And so if the couplings become larger and larger, and so A becomes more and more negative, you just go away from the domain in which these things make sense. Anyway, so and then in 3 minus epsilon dimensions, there's a similar story. You can analyze sextic potentials. Even in the ON case, there are 2 invariant polynomials, namely phi squared and phi to the 4th, or phi squared all squared. So you have to tune both of those to 0 to get to a fixed point. And results for the beta functions can be worked out. In theory, you can analyze such theories a bit using the bootstrap and so on. The fixed points only exist below 3 dimensions, and again you can work out the large. So it's a somewhat similar story, but nevertheless the behavior at large n is somewhat different from what you get in the 4-dimensional case. Well, maybe these results are not so interesting from a more mathematical audience. I mean, there's various scaling limits in which you can take n to be large and the theory becomes tractable, but nevertheless this is not been explored in any great detail. Okay, in 4 minus epsilon dimensions, again, limits when n is very large, you can more or less solve the theories exactly, at least in the leading large n limit, but so I think I'll miss this out. So, concluding as to my last slide, whenever you've got a large number of scalar fields, you can have many different fixed points, and they should all correspond to conformal field theories, potentially in 3 dimensions. And then if you perturb them, they flow to other operators. All these operators have Z2 symmetry in them because that's built in from the start, because you're dealing with quartic polynomials when you do this kind of expansion. This can be broken if phi cubed operators become significant, because as you change the dimension, the phi cubed operators could potentially increase in dimension such that they become mixed up with the phi to the 4th operators, and in which case the Z2 symmetry would no longer be valid at the fixed point. But these are dropped in the standard epsilon expansion. So one of the things one would potentially like to ask is, are there fixed points in 3 dimensions which do not have a built-in Z2 symmetry? Because those are theories which would not be accessible in the standard epsilon expansion. So we don't really know the answer to that question as yet. I mean, there are theories involved with what's called the Q-state Potts model, which don't have a Z2 symmetry, but quite how they contribute in 3 dimensions is another matter. So the ultimate aim in all this would be to sort of have a good understanding of what are the fixed points, for instance, in theories in 3 dimensions, which we presently don't really know about. But the final sentence is just that for anybody looking at quartic polynomial theories in 3 dimensions, there is a lot you could potentially do in terms of looking at theories with more than one field and saying whether or not you can find fixed points in a sort of better controlled sense than the way that I've been describing them. Well, thank you.
There is time for some.
Yeah.
I suppose you could do exactly the same thing for long-range models, where you have a fractional.
Yeah. I mean, of course, what I've described is all in the context of short-range models.
But my question is, if you do that in the long-range case, would you have the existence of A functions?
I'm not sure. I just don't know the answer to that question, because I can see that there would be other. I mean, the theories for which I know the A function exists are all ones which are essentially local theories, where we have things which are involving, fields at the same point with a finite number of derivatives, or at least effectively just 2 derivatives. So I don't know the answer to that. I mean, the A function is to a certain extent like a Lyapunov function, that it controls the behavior under RG flow. So it's certainly the case that if you take non-unitary theories, you can construct situations in which you get RG flows which end up on limit cycles. But that's not the case in the unitary thing. So the nice feature about the existence of an A function, which you can more or less prove in 4 dimensions, and then there are arguments which it can be extended to 3 dimensions, is that it removes the possibility of complicated flows in the under the RG flow. You just end up on fixed points. So, but I don't know the answer. Long range is a more complicated situation.
But I mean, in certain ranges, it is unitary.
Well, it's not so much unitary. Well, yeah. I mean, I'm not saying it isn't unitary, but I'm just saying is that whether or not you can come up with the. I mean, how you define A. I mean, I just put it in by hand, but nevertheless, A is related to certain anomalies which appear in a curve space background, which are essentially topological in character, which exist in 4 dimensions. There's no really watertight definition of A other than in 4 dimensions, or 6 dimensions for that matter. There is no watertight definition of A in 3 dimensions, but you can kind of construct it by hand, at least in the epsilon expansion.
There is another.
When you define the A function you have a second order term and a third order.
Sure, but there will be arbitrary orders in principle.
Yeah, of course.
Yeah.
So I was curious to understand why the third order is 1 as coefficient. So maybe there is some rescaling, but in principle should be some.
Well, I've got rid of various factors of 4 pi by rescaling the couplings, but nevertheless, that's what it is, right? It depends upon the fact, if we go back a long way, I don't know whether I actually wrote it down.
Beginning. Yes, there.
Well,
It's 1, yes.
well, that's because that's what the beta function is, right? I mean, if you like, if I know what beta ijkl is, which I didn't actually write down, it is 1, right? I mean, I think that's what calculation tells you in a way. I mean, I think in the example that I gave in 6 dimensions, one of them anyway. This one here. So there, I mean, that's the result if you look at the A function in 6 minus epsilon dimensions, and there one of the terms has -1, the other one has a quarter, right? I mean, it is what it is, right?
Exactly what it is.
Yeah, I mean, obviously as you go to higher orders there'll be more complicated things, but I only gave the lowest order one just for illustrative purposes. And I should say that when you look at the gradient flow equation, it becomes more complicated than the one I've written down once you go to higher orders. But the argument for using the epsilon expansion is that it's qualitatively correct. That, you know, working to first order is clearly a bad approximation, but nevertheless, if you can find a fixed point to first order, then hopefully you can extend it to higher orders. So it should qualitatively give you the structure of potential fixed points in the theory.
Okay, so the last question.
Yeah.
Were the operator products explored by these techniques at these fixed points?
Yeah, sure. We could. Well, of course, one of the standard thing in the bootstrap is to work out the 3-point functions of the operators, but you can also calculate them, and that wasn't done historically in the 1970s, but in the last few years it has been done quite extensively, just for the purposes of comparison. I mean, one of the reasons for the recent resurgence is that you, on the one side you have the bootstrap, and you want to compare it with something, and you can't really compare it with physical data, but you can compare it with the epsilon expansion, and that's why people have, they've actually used the whole bootstrap framework to actually compute stuff in the epsilon expansion, you know, to quite higher orders and so on. So, I mean, that is one of the sort of, you know, huge incentives. There's a sort of interplay between the epsilon expansion and the bootstrap.
Okay. So, thank you once more.